Hello, Chemistry 12. This is Mr. Chan, and what I wanted to do was talk about the last section in solubility equilibrium. And for today, what I want to do is take a look at section 3.10, something called the common ion effect. So what is the common ion effect? Is basically you're adding an ion that will shift the equilibrium. Okay? So basically is Le Chatelier's principle. Now, but one thing you want to be aware of, since we're talking about a solid in equilibrium with its ions in a solution or a saturated solution, a couple of things we have to consider. So when you have a solid going into ions, it's called the dissolving reaction. And when we have the ions forming a solid, it's called the crystallization. Okay? So when you take a look down here, it says in the last couple of paragraphs, therefore, if we can increase the rate of dissolving, basically you're saying that the solubility increases right here. So if you increase the rate of dissolving, solubility of the solid increases because you're producing more ions. If you are increasing the rate of crystallization, you're saying that the solubility is decreasing. Okay? Now, you can think of it like this in this aspect. Here, if we're looking at the equilibrium, notice here it's shifting to the products. And in here, in this case, you're shifting to reactants. So basically, we are using the terms dissolving and crystallization as another way to express shifting to products or shifting to reactants. Now, if you look at the next page, okay, this is section 3.10. So they talk about how can you decrease the solubility of a salt. So basically, another way you could think of it is shift equilibrium to the left. So in this case, if you go through the examples here, it's pretty straightforward. It says if you increase the concentration of one of the ions, okay, the equilibrium will shift so to use up some of the added ions and cause more solid to form. So if you take a look at the original equilibrium here of silver chloride, breaks apart into silver and chlorine, what we can do is we can add the Ag, increase the Ag, the silver ion concentration, or increase the chlorine ion concentration. And what that does is that it increases the products. Notice this is bolded. And so as a result, the equilibrium shifts to the left. Now, if we continue on, what's a way to decrease the solubility of a salt or increase the solubility of a salt? Basically, we want to shift equilibrium to the right. Now, this is a little bit more complex. Why we can do this in a way to increase the solubility is by decreasing one of the concentrations of the ions. In this case, by adding some ion which precipitates the Ag present. So how does that work? Is in this scenario, notice you have two equilibriums involving silver. So the original silver chloride breaks apart to silver and chlorine ions, and a precipitation reaction where silver reacts with sulfur. So in this case, you could think of it like this. Because Ag plus is used in two reactions, the one for the silver chloride equilibrium and the other for the silver sulfide, therefore, concentration of Ag plus decreases. And what happens is that the silver chloride solid will dissolve more. Now, you folks have experienced this before. When we did the chemical equilibrium, remember we did a lab and I said, oh, what happened was the OH minus one, you produced yellow with crap. Remember that precipitate. And then some of you, remember we had read something about step 8, where precipitate of FeOH3 was formed. Now, this is an example of common ion because of the fact that the Fe, if we take a look back at our equation, was used not only for the FeSCN, but the Fe was also used for the FeOH3. So since Fe was used in both of the equations, this is what we call common ion. So in this case, for this scenario, the common ion is not adding additional ions, but what you're doing is you're using the same ions for 2 or 3 different reactions. Okay? Now, what I wanted to do was go through an example of how would you calculate this. Okay, so first of all right, so how would we calculate, like, how would we do something like this? Okay, so let's say question number 86. Arrange the concentrations of following solutions such that NaBr has a decreased solubility in them. Explain your choices. Again, in this particular scenario, how would you answer this question? Is you would look for the common ion. Oopsie. Look for common ion. And you have to think of it. Does it add ions or use it up? Okay, so that's what you have to think of. Now, let me give you an example of a typical calculation in regards to how would we do common ion effect. So let's say, for example, calculate the solubility of, let's say what? Of, let's say, MgCO3 in 0.20 molarity Na2CO3. And the KSP of MgCO3 is equal to 6.8 times 10 to the negative 6. Now, again, we're calculating the solubility. So we're calculating how much dissolved. So how do we set this up? We set it up like how you've been doing it before. So let's say you have MgCO3 is in equilibrium with Mg plus and CO3 minus 2. Now, we set up our ice tables, and here is where the difference is in terms of the setup. So you have ice. Okay. Now, here, whoopsie. Here is 0. Okay. Now, in this case, the CO3 is 0.20 molarity. That's the initial concentration. Now, why is it 0.20 molarity? Because it comes from your sodium carbonate. Okay? So in this case, the sodium carbonate produces CO3, which is the common ion, and that's how we get this concentration. Now, how did I know it's 0.2? Because you break it apart into dissociation, it is, if we break this apart, it's 1 to 1 for CO3, and so you get 0.2 molarity. In this case, again, what you have is you have plus X. Here will be plus X. Oopsie. And then what you get is X 0.20 plus X. And so you have KSP is equal to concentration of Mg plus 2, concentration of CO3 minus 2. And so you get 6.8 times 10 to the negative, what is it? Negative 6, which is equal to X 0.2 plus X. Now, you can expand this and use a quadratic formula, but again, an easier way would be pretend that the change in X you can ignore. You can think, why can you ignore it? Is because you can think of it, the amount of ions from the MgCO3 dissociating is so small. How can you tell? The KSP is so small. So then you have, if we stick with red, so we have 6.8 times 10 to the negative 6 is equal to 0.2x. So x will be, if I do my calculation here, okay, 6.8 e to the negative 6 divided by 0.2. So I get 3.4 times 10 to the negative 5. And this x is how much dissolved? Okay. All right, now, by calculating this x, now you know why we can ignore the plus x, because notice the value is so small here, 3.4 times 10 to the negative 5. If we went back up here and looked at this equation, the 3.4 times 10 to the negative 5 would have little to no effect on the equilibrium concentration. All right, ladies and gentlemen, so that is just a simple common ion effect. All right, if you have any questions, please feel free to ask me when we see you in class. All right, folks, thank you very much. Have a good day. Bye-bye.